In this section, I just wanted to take a look at some visual perception. And off the top of my head, I can think of some nice graphics papers which show some pictures, but I thought I'd do a quick literature review and find out, has anything really been done in, what makes a nice display, what will actually be beneficial for augmented reality in surgery. So I'm thinking of anything to do with laparoscopic or endoscopic displays, so monitor-based systems. What are people doing to make it a convincing 3D environment? Long story short, next to nothing. So I found this 2017 paper by Wang, and they reference these two papers as the only other two papers they could find, and I certainly don't know of any others. So obviously I kind of wish this would be more of a discussion live, but we've set to this other paper. But I think this one's worth going through, mainly because I couldn't really find a better paper that had done an evaluation of their usability. So the biggest problem with augmented reality currently in terms of visualization is however you draw the augmented graphics, when it's run on top of a live video, almost any kind of artificial graphic has the tendency to pop out in front. So even if you render it at the correct depth and the correct size, it just looks like it's on top of the video. So this paper was trying to evaluate, which type of visualization is best for depth perception. So let's switch to the paper. So stereoscopic augmented reality visualization for depth perception in endoscopic surgery. I'll just quickly jump to a picture so we can see what we're doing. So scrolling down the paper here, this one seems to capture the general gist in one shot. So they've created a kidney phantom, presumably from a CT scan, but I can't remember. So they've got the size of the kidney and they've got the vasculature, and they want to try and work out which of the commonly available visualizations looks best and can be demonstrated to be the best. So in this left column here, they've done on the top row is just this tumor, and on the bottom row are vessels. This left one here is what you call alpha blending, where you blend the transparency of the video and of the rendered display. The second one is a fixed kind of window, so you define the center of the screen maybe, and you just cut away the video in this section here, and you render the virtual world. This one I've never heard of. Is sort of I mean, people have done this before, and I think there's even a paper by Eddie that said actually just rendering these artificial sort of CT scans using surface rendering is bad, and depth perception was better when they actually put a texture on top of it. I presume that's where this middle one's coming from, but they're basically rendering random dots on top of it. This third one is this kind of blended or faded in window. It's called a transparency mask. And this last column here is they're calling a ghosting method. I'll come back to that, but basically what you try and do is you run feature detection on the video, and where there are features on the video you tend to preserve them, and only when there's kind of featureless areas do you allow the transparency to shine through. So anyway, they've got these methods and they try to evaluate them. Can I pause this thing? Let's have a quick look at the controls. Probably not. So they try to evaluate them by giving different tasks. They do a phantom study and then they do a porcine study. And the questions are mainly based around which one do they like. What they did do though was more quantitative, because they're using a stereoscopic display here. they would go through the process of taking two different types of rendering and then switching between them, and the user had to pick, you know, which one of these was deeper than the other. So a side-by-side comparison to see if they could actually detect which one was correctly, which one was deeper and which one was closer. So which one was further away and which one was closer. So I'll go back now and we'll talk a bit more about the general overview of the system that they're trying to build. So here summarizes the system, and hopefully a lot of this should, and now at the end of the course, be quite familiar. So they take the video camera, they calibrate it. Here they show a load of chessboards as usual. Calibrate your camera. They also take the CT scan and segment out the tumour. They've got this phantomy thing here, and they've put extra texture on because it's just 3D printed. This means they then take a number of views and they can mosaic them together, or rather for each view they can do stereo reconstruction and then stick the point clouds together. So basically you create a set of point clouds that represent the physical thing in front of the camera, and you then register that to the preoperative scan using ICP and stick it on the screen. So most of these technologies we have now covered. Here's they're just explaining more about the registration. Here they give the formula for that alpha blending. It's fairly straightforward. For example, if you just say there's the overlay in the video and you have this parameter alpha between 0 and 1. So if alpha's half, you have half video and half overlay and so on. It's just a linear kind of blending. This virtual window, so they do go into detail of how exactly they create them all. Just to note here, they're using a stereoscopic display, which I've never done before. I'm just guessing because I'm reading this. An auto stereoscopic display has like little lenses on top of it, which you then create different renderings with slightly different stereo offsets, such that when you look at this grid, one eye sees one picture and another eye sees another picture. So I'm guessing that they just have to render 9 of these different views and interlace them somehow, but we can skip that for now. This is where they explain the ghosting. You basically look at edges, color difference and contrast, and this ghosting map tells you essentially when you can permit transparency or not in the video image. So the perception tests, here we go. It was basically based on questionnaires, and they were asked to pick which one they preferred for vessels, which one they picked for tumours. They did a relative depth test, and this is where they're showing which of their methods worked the best. I'm going to skim over it quite quickly. You can read this after the lecture. So this is the summary of their different take-home messages. So transparent overlay was just very simple and conceptually, but it just didn't perform well at all, which interestingly is what we're doing on the Smart Liver for now, because we haven't really invested much effort in the actual visualization yet. People didn't like the virtual window approach, the random dot approach they just didn't like at all. And then the transparent mask and the ghosting method seem to be the preferred one. And I've seen other papers which also seem to suggest that this kind of faded in circle, here we go, this one here, where you've got a nice blended edge and you can see into the virtual world in the middle, seems to be the one to go for. And that was their general conclusion of that. So this is just a very quick summary of the paper, and I'll leave you to read it at your leisure, because it is pretty much one of the only kind of evaluations in this space. Our laparoscopic stack doesn't have an auto stereoscopic display. It has a stereo display with glasses, just like in the movies. So they're polarized lenses. so the same sort of thing could be applied to that. I don't see it's a big difference between auto stereoscopic and polarized stereo. So that is an evaluation, and that is pretty much what people are doing right now in this kind of evaluation. Now, I did think as I look at it that maybe if you did volume rendering you could get such fantastic realism, but the reason we haven't had that up to date is because the volume rendering engines are too slow. But now in 2018 NVIDIA released the real-time volume rendering, so maybe these things could change. But it still doesn't get around the fact that even if you can do absolutely photorealistic rendering, what does the user expect to see at different stages of an operation? So I'm fairly sure that you could conquer the actual rendering, but at the moment even the user requirements are not clear, and what we think as technologists would be useful or a really cool set of graphics could just be thoroughly confusing to a surgeon who's got other things on his mind. So this is again where we need usability analysis. We need input from all sorts of different people, graphic designers, surgeons. It's not an easy question, even if you can do fantastic graphics. Anyway, that's the summary, and I would suggest reading it at your leisure to get a feel of where the field is at in terms of visualization and evaluation of that.